I want to talk about some operations on Taylor series. Last time I gave you 4 Taylor series to commit to memory. This was one of them. And obviously, these aren't the only Taylor series you're going to encounter in your life, but these are 4 very important ones, and you will build up a personal library of Taylor series depending on how often you use them. But let's say we happen to have committed this Taylor series to memory, and we want the Taylor series around x equals 0 for e to the x squared. You have 2 options here. One option is to go back to the definition of Taylor series, and you could call this function f of x. And you could take f prime of x, f double prime of x, f triple prime of x after the 4th, the 4th derivative of x and the 5th, and so on until you spot a pattern. And then you can plug in x equals 0 for each of those and work out the coefficients for the Taylor series. That is quite laborious. We have a shortcut here using composition. If you happen to know the Taylor series for e to the x is this, you can just go ahead and put an x squared in everywhere you have an e to the x. Everywhere you have an x over here. So 1 plus, instead of the Taylor series of e to the x, we just have an x there. So the Taylor series of e to the x squared, we just put an x squared there. We just put an x squared right there in for x. So x squared cubed plus x squared to the 4th, and so on. We just put an x squared in everywhere we saw an x in this original Taylor series. And we have 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus x to the 8th over 4 factorial, and so on, going off to infinity. That is a significant shortcut. I also would like to remind you, and again, this is something that you studied in calculus too, that it is possible to take the derivative of and antiderivative of Taylor series term by term. Let's go ahead and take the derivative of the Taylor series for e to the x. So that we'll take the derivative of 1 plus x squared plus x cubed plus x to the 4th. Oh, sorry, that's not the Taylor series of e to the x. Taylor series of e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, and so on, forever. Well, the derivative of 1 is just 0. The derivative of x is 1. The derivative of x squared over 2 factorial is 2 times x to the 1 over 2 factorial. The derivative of x cubed over 3 factorial is 3x squared over 3 factorial. The derivative of x to the 4th over 4 factorial is 4x cubed over 4 factorial, and this goes on forever. That should be a plus sign. So let's simplify here. Here we have 1. The 2 cancels with the 2 factorial on the bottom, just leaving us with 2 factorial is just 2. That just leaves us with x. 3 here cancels with the 3 factorial on the bottom. 3 factorial is 3 times 2 times 1. So the 3's cancel, and you're just left with 2 factorial. X squared over 2 factorial. The 4 cancels with the 4 and the 4 factorial, so we're just left with the 3 factorial. X cubed over 3 factorial plus, and so on forever. And you have 1 plus x squared plus x squared over 2 factorial plus x cubed over 3 factorial. In other words, you have the original Taylor series for e to the x, which isn't surprising because the derivative of e to the x is e to the x. If you go ahead and take the derivative of sine x, you know you get cosine x. So go ahead and take the derivative of the Taylor series for sine x. So you recall the Taylor series for sine x. This is one of the Taylor series that you can commit to memory. So sine x, we know, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the minus x to the 7th over 7 factorial plus and so on, minus plus minus. Okay. If you go ahead and take the derivative of the Taylor series for sine x, you will, I guarantee you, get the Taylor series for cosine of x. If you go ahead and take the derivative of the Taylor series for cosine of x, I guarantee you will get the Taylor series for negative sine x. You can do this with derivative. You can do this with antiderivative also. You can also take antiderivatives term by term. Works out very nicely. So this provides you with a significant shortcut for computing the Taylor series of several important functions.